right, for those of you that don't know, you're lucky that you don't know. No. No, so David Redden is the current chair of the Department of Biostats, but he has been, for many, many, many years, an excellent collaborator for investigators at all levels. He is huge on training, huge on experience, huge on everything, but it's very much all about helping people with their science, helping people with their careers, gives very much of his own time, more than he has available, but also works very closely with other folks within the Biostats department. And he's got colleagues at Tulane that he works with, but if you ever have a bad experience with a biostatistician, which is rare, but if it happens, let him know, because he views it very much as a collaborative team science approach. And as investigators, you carry some of that weight as well, that you come in and not just say, here's the data, tell me what I want. He wants it to be an interactive learning experience. But with that, I'll hand the floor over to you.
All right.
And we go to Tulane, and we can minimize however you want.
Where is the minimum? I'll let you. Then I'll bring it up and we'll go. So I appreciate the introduction. Let me set the context for today.
Get your jump.
Oh, I don't have the jump up right with me. Hang on. Sorry?
No, that's not me. I should have saved it.
No. Let me get one for Jamie. Or can you get one for Jamie real quick?
I've got it.
All right, let me just pull this up. You got it? Or?
I'll get it. You go ahead and chat.
I'll go on and chat. Thank you. Sorry, guys. For everybody who knows me, I have 3 daughters. 2 of them are teenagers, and let's just say we had a little bit of a interaction between mom and the middle one this morning, so I'm a little bit off schedule. So
Happy Father's Day.
Happy Father's Day. Yeah, Happy Father's Day. So let me talk to you about statistics, and I'll be very straightforward. And you'll see this in my talk. I am a firm believer that the majority of statistics and biostatistics is actually taught in an incorrect manner. So this talk today, now when Dr. Levitan comes in next week, she will start drilling down into designs. Today, I want to really talk about the forest, not the trees. When we do statistics and when we introduce statistics, what we typically do is we run you right into descriptive statistics. Then we run you right into probability. Then we run you right into, oh, the central limit theorem, you gotta understand this. And then the next thing you know, you're doing all these hypothesis tests. And for the life of me, for the first, I came out with a bachelor's in mathematics and had no clue what they were trying to do. Because it was memorize, memorize, move, 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 move. And I'll be very blunt, it really wasn't until probably 18 months into my graduate program that it started to click how all these components are actually synergizing together. So what I want to do today is simply back up and take the time to talk about first principles of statistics, that it will always begin with and end most with me. The first thing I have to understand as a collaborative statistician is, what is your hypothesis? What are you measuring? And how are you measuring it? If you had been in the room just 2 days ago, we had a set of statisticians in here meeting with MDs, meeting with graduate students, meeting with fellows in consultation, and you could have been bird on my shoulder. And when the person sat down, the very first thing I said is, just explain to me, what are you measuring? Help me know what you're measuring. Because from there, that tells me what statistics I can bring to bear and how I can go about helping you to address the questions. But I'm also going to give you plenty of experience or plenty of comments from horror stories from my career so that you understand where I'm going. So, guys, you got to understand, if I ever write a textbook, if I ever get around to it, it's going to be like a book you've never seen before. So I've already kind of done the brief overview of statistical inference before we got going, just this chatter back and forth. But I'm going to tell you why probability should come first in every statistical textbook. We don't do that. We come in and we start teaching you, oh, this is how you summarize data. Here's the sample mean. Here's the sample variance. And you're trying to get your head around what are these things measuring, but what you're missing is those things are an indicator of something that is hidden from your view. You should always think of statistics as trying to estimate something that is technically hidden from view, that is controlling either your experiment or informing your experiment or informing your measurements, all of these things. So that's what I'm going to talk about, the basic probability distributions. Technically, you're going to pretty much get a summary of a full semester of statistics in about 1 hour. Tell you about those, and I will emphasize over and over and over. The reason I first ask you what you're measuring is because I then have to understand what statistics I'm moving toward, and then from those statistics, I know what I can do. Talk to you about the central limit theorem to get you to understand every statistic I ever measure, I recognize follows what's called a probability distribution. Now, I may have a hard time linking that measurement directly to a probability distribution, but that's my job. I've got to ask every day, you've conducted this experiment. The data has been realized from that experiment. Now, how likely am I to have observed this data under specific conditions or specific hypotheses? That's the whole foundation of inferential statistics, right there. But you understand it's building off of nothing more than the scientific method. State the hypotheses, collect the data, analyze the data, draw a conclusion. I often joke, but it's absolutely true. I learned my whole career in 7th grade, science. State the hypotheses, collect the data, analyze the data, draw the conclusions. Where modern statistics falls down and implodes upon itself is that last step, actually. And there's a huge pushback in the past 5 years, and in my career, this is probably the 3rd pushback I've seen about are we over-interpreting. We're going to talk about the key terms correctly defined. I'm going to tell you the absolute truth. I'm not going to be able to get through all of this. We have to be very careful because we have a 9:30 conference call in here. I'm going to give you the truth that you'll never find in a textbook. Modern statistics does not actually come down to any specific one set of statistical theory. We had 2 camps in the 1920s, 1930s, 1940s, Fisher and Neyman. Pearson. Tell you about that history, and I'll tell you why modern statistics is so confusing. Because what we did is we couldn't decide who was right. We smashed them together and published it in every textbook. We blended everything. But they came at it from such different angles, it confuses people. And I think half the confusion about statistics is right there. I'm going to give you some examples of power and correlation, but we're probably not going to get all the way through it. I might have to come back in a few weeks. So you open any textbook, you get the following. I can guarantee you, I can go into my office right now, pull 5 right off the shelf. Every one of them does this exact same thing. Yes.
So, ask questions throughout though.
Oh yes.
If you don't understand something, it's likely someone else does it. So don't be afraid. I just want to make sure.
Yeah, that's true. And the other thing is, again, Again, I gave you the context of my morning already, so you know I've already got a little bit of adrenaline running. You probably know I'm over-caffeinated. But so it's falling into lecture style. I actually prefer conversation. You know, this is why I've always gone back, and I will never give up on the collaboration or the team science. I love learning what people are doing and then being able to use my training to enhance it and to have this synergistic effect. So, you know, if you open them up, it's just broken into thirds. You get, okay, here's a data set. Here's how you calculate the sample mean. Here's how you calculate the average. Here's how you calculate the quartiles. Here's how you calculate the sample variance. Here's how you get the median. Here's the interquartile range. But there's no, well, okay, so I understand how to summarize data. And then I get this really bizarre switch, and I turn, and all of a sudden, here comes all these probability problems, which most people, from my experience, most of the students do not really enjoy. They don't like necessarily the probability problems, and there's kind of like, well, why did I start with data, and why did I jump to probability? And then you come back to the point of now I'm doing hypothesis test. And there's no quilting together of these disjoint concepts. And then we get into hypothesis testing. And I want to emphasize, by statistical inference, I mean you're going to get a p-value. And if in every lecture, I was taught this very early in my career, and every time you get up and you speak, you emphasize over and over and say, this is the point. If there's one thing you walk out of here with, what is the key thing? Well, there are two key things to walk out of here with today. If you've got a question about statistics, talk to a methodologist. I'm not going to say statistician. Talk to a methodologist. Reach out. Find them. You are not supposed to be an expert in everything. Go to someone and say, can you help me think these things through? Can you help me estimate these? The second thing I need you to understand is what a p-value really is and what it's not. It's causing great problems statistically. And I think the majority of people, and I will say this very bluntly, and yes, I'm being recorded, I know for a fact the majority of my most senior collaborative investigators who hold R01s over-interpret a p-value. You got to realize it's just one piece of evidence. It's not the only evidence out there. But if I talk about null hypothesis significance testing, I mean, you're going to go. So when I teach, I do it very differently. I start with probability. And I start with probability for a very specific reason. And I say, okay, probability first, guys. Understand this. Then let's talk about statistics. And then let's talk about how statistical inference is born out of the probability distributions. Okay? And this is the way David thinks. It actually drives a lot of people insane that I think this way. Whenever you come to me and you say, okay, I have, and this happens a fair amount, I would recommend don't do this. Talk to me before you collect your data. As you're designing it, we need to be there. I can discuss with you different aspects of design and approaches that will, at the end of the day, make a little bit of an investment in the front end can save you a lot of pain at the end. But when you come to me and we start discussing, the very first thing that's going on in the back of my mind is, what's the probability distribution? You're going to be thinking about the observations and the data. You're going to laugh at this. The statistician's not sitting here thinking about the data. I'm thinking about what hidden mathematical model generated that data. That's what I think about. When I think, y'all are going to laugh. I enjoy beer. Okay, I enjoy beer. But I also, when I think about, and I pick up a six-pack of beer, it will typically say 6.2% alcohol by volume, right? But I know that if I actually measured every one of those bottles with specific gravity, I doubt every one of them is going to be exactly 6.2 on the dot. There is variation. There's going, just by the system, there's a system that's out there by which they're filling the bottles. There's going to be some variation. I want to know, how variable is that? What's the distribution behind it? When we talk about hurricanes, one of my favorite things, every year we get the forecast for the upcoming hurricane season. Ever notice that it really isn't that big of a difference from the previous year? They keep giving you pretty much the rolling mean of the previous year. Now they're paying attention, but the bottom line is they've studied patterns over time, but they know that there's a probability distribution out there that literally can help us model the number of hurricanes. And so we try to model it and we go from there. But technically, the observation is the number of hurricanes in a given year. What we're trying to really study is the distribution behind that. And the real great question lately, given climate change, and I'll go on and say global warming, the question is, has that probability distribution changed? That's a key scientific question. It's not what we're asking when we study the data is, we're not asking has the data changed. We're asking, has there been a shift in the underlying probability distribution, the hidden mathematical model behind it? And from that, you will get down to statistical inference. But the whole issue is you collect the data so that you get to statistical inference, and the inference is about the probability distribution at all times. You're always studying that. Examples, nature. Of course we do hurricanes, tornadoes, rainfall. Classic example with my dad. You've got to understand that all physiological measures are technically following a probability distribution. All right, let me ask you this. In Fahrenheit, please, body temperature is what? Healthy body temperature is what?
98.6.
Everyone in this room at 98.6? Mm-hmm. Do we all run at 98.6?
No.
That's the population average. That's where the probability distribution centers. And we define fever as when you have deviated too far from the center of the population. It's a fundamental thing. It's basic statistics. But when my dad was ill, my dad would go in the hospital repeatedly due to his slow kidney failure. But I would ask consistently, what's Dad's temperature? And they'd come back, oh, he's fine, he's now 97.5. I said, y'all need to culture him. I'm afraid he's got an infection. And the nurse would look at me like I'd lost my mind. And I would explain, for all of my dad's adult life since I've been here, my father always has had a body temperature lower than 98.6. I never have seen him at any doctor's visit have a body temperature anywhere near 98.6. If he's above 97, something's not right. And they'd look at me like I'd lost my mind. And then usually 2 days later, they would say he has another infection. So you've got to understand, this is why when you study history, you collect data to draw some judgments about what's the distribution behind it. My favorite one is the bag of M&Ms. That's a classic probability distribution. So there's plenty of things. Anytime somebody brings me anything, anytime I observe anything, I think to myself, what's the probability distribution? And you don't have to understand all these. You have to have a colleague who has studied these for years. The key thing is this. Variation underpins the concept of the probability distribution. If it's going to vary, such as a person's body temperature, the pressure among the 4 tires on my car, the amount of alcohol per volume of my beer, if it's variation, if you think it can vary, it moves from measurement to measurement, there's a probability distribution somewhere. And once you've gone there, you need to start thinking about how do we summarize that distribution How do we make judgments about that distribution? That's the fundamental of statistics. And this is the way collaborative statisticians are going to think about it. And I want to back up too. And here's the cool thing about it. The probability distribution is like a parent in the sense that the data must inherit the characteristics of the probability distribution that is generating it. That's the key thing. The only reason I ever teach you to graph data and to do a histogram is I know the data must inherit the characteristics of the probability distribution. Therefore, if I can see the shape of the data, I have a judgment about the shape of the probability distribution that generated it. From studying the shape, I can map it to the, I know certain distributions have to be bell-shaped. I know certain distributions have to be skewed. So simply looking at the data helps me understand something of the nature of the hidden mathematical model behind it. Same thing. Wherever the center of the probability distribution is, because it passes its characteristics into the data, I can get an educated guess of where the center of the probability distribution is by looking at the center of the data. That's why I teach you to look at the sample mean. Sample mean just helps me guess where the probability distribution center is. The reason I ask you to measure variance out of the data is because the probability distribution had to pass its characteristics to the data. By estimating the sample variance, I get a guess about how variable the probability distribution is. These are the things, this is why we do it. It's the data is helping me, my favorite word, infer or guess something about the probability. And yes, that's what I do for a living. I make a lot of guesses. Okay? Okay. And have we locked up? No, we're back. So the common statistical distributions. And again, we get into a section in the textbooks where they just hit you left and right. The key thing is simply this, folks. The reason I need to know the distributions is because I need to take the data and map it back up. There are certain things that follow the Bell IQ. I know for a fact the way it was designed, centered at 100, standard deviation or variability of 10. Height, some of my favorite Poisson distribution. A Poisson distribution is the count over time or the count per something. If you hear per, you need to stop and think, oh, maybe a Poisson. Classic teaching examples. We originally discovered the Poisson naturally in nature by studying the number of live yeast left in a vat of beer after fermentation. So per vat, we would find X number of live yeast. The other things that follow a Poisson distribution by teaching examples are the number of shipwrecks per square mile on the bottom of the Atlantic, the number of texts that you will receive per hour today could be approximated by Poisson. Binomial, the number of successes, failures, we use the binomial a lot in clinical trials, especially with regard to toxicity. Did the person have a toxic response to the drug? Phase 2 trials, we use a lot of binomial distributions and try to estimate that binomial, the number of people who will respond to this drug. I like the multinomial because it helps me with genotypes, haplotypes. It also is my favorite teaching example in the honors undergraduate class. It's bag of M&Ms follows multinomial distribution. And we teach how to do estimation precisely using the bag of M&Ms. So again, the only purpose I put this up, usually when I teach even the graduate courses, I have to keep saying, please don't get absorbed into all the Greek symbols. Please don't try to memorize all these formulas. It's a waste of your time. All I'm asking you to do is to remember, if you have estimated a statistic, such as a sample mean, or a sample variance, or a correlation, you've actually estimated a characteristic out of a probability distribution. The mindset you have to ask yourself is this: how do the probability distributions relate to my experiment? So let's talk about this for just 1 minute before we race ahead. Suppose you're doing you come to me and you say, David, I would like to do a 2-group study. We're going to do intervention A here in this group, and I want to do intervention B over here. And I need to show that the interventions produce different outcomes. Do you know what you just technically asked me? You're thinking that way, and in the back of my head, I think, okay, you want to do experiment A, that's going to create that, and from there, we're going to have a probability distribution that I will call probability distribution A. Because probability distribution A is going to be the one that generates the data. Then you're going to have this other one where you're going to do something different, and because you're doing something different, technically, you're asking, is there a probability distribution B? You're asking me when you do the experiment, David, can you demonstrate for me that after I've done this that I actually have been working with 2 distributions instead of 1? Because if there's no difference between intervention A and intervention B, at the end of the day, you're only playing with 1 probability distribution. So really, from a statistical standpoint, your experiment is asking me, you're asking, do the interventions differ? And my evidence for the interventions differ is they differ if the probability distributions can be demonstrated that there's evidence that there's 2. That's what it boils down to. So these things here, X bar, S squared. You know what? Here's the summary of all descriptive statistics. X bar helps me know where the center of the problem. It tells me where the center of the data is. It's a precise estimate of where the center of the data is. The only reason I care about is because it also helps me know where the center of the probability distribution is. That's it. And the only reason I care about the sample variance is because it helps me understand how variable the probability distribution is. Now, if X bar 1, if X bar from group A is far away from the X bar of group B, or the sample mean for group A is far away from the sample mean for group B, do you believe that they can be 1 probability distribution? Remember what I said to you to begin with. Data must inherit the characteristics from its probability distribution. So if there's 1 probability distribution, there's only 1 hiding out there. More than likely, those 2 estimates will be really close to each other. When they're far apart, that's going to help me believe that there are actually 2 out there. That's the fundamental of statistics. I just gave you the whole semester in pretty much 1 example. And what I use, why I use probability to say, how likely is it that I could get 2 sample means so far apart if there were really only 1? And if that's rare, then I believe we've got reasonable evidence to say that there's 2 distributions. And I used a key word, rare. The way statisticians judge what is rare is the laws of probability. Okay? All right, so there are some cool facts. I've got to watch my clock. Because data inherits the characteristics from probability distributions, statistics can be used to infer characteristics. Under certain assumptions, you will always know how the descriptive statistics should behave and that it will follow a probability distribution itself. And the mind-blowing fact is that under a lot of cases, the statistic may follow a distribution that is different than what generated it. And that's probably the hardest thing for people to, when they get introduced into statistics, to get their head around. Your data may have actually come from a binomial distribution. But if you have asked me to summarize it with a sample mean, then the sample mean of the data may follow the normal distribution instead. And this is why you sit down with statisticians. One of the things that people don't know is we spend a lot of time in the math department understanding all the theory behind the way these things converge from a calculus point of view so that we will be able to correctly link the statistic has to follow this distribution. Okay? And the other thing that is a key thing that I do true false for in the honors class, statistics do follow probability distributions. Data follow probability distributions, but when I summarize the data and calculate it all the way down to a sample statistic, that sample statistic also has to follow a probability distribution. Because let me put it this way. Here's a question for you. Or just kind of like a thought experiment for you. Let me give you a good thought experiment on this one. All right? If I came in and I randomly picked 10 of you to calculate an X bar on you with regard to, let's say, blood pressure today, and then I came back tomorrow and I calculated and I came down to a sample mean, right? Then I came back and did the exact same thing again tomorrow. Would I get the exact same number? Do you think I'd come back to the exact same number? No. And what did I tell you? If something varies, if something that I'm measuring varies, then there has to be a probability distribution. So the fact that I'm studying X bars and just getting the sample mean over and over, but it's going to vary, means that that statistic also has to be governed by a probability distribution. Okay? Keep this in mind. This is a key thing. If you would study this diagram and keep this diagram around, it will save you a lot of heartache. Because a lot of times we get so obsessed with the bottom piece, the statistics, the inference, we rush to that we, again, miss the forest for the trees. I want you to get the forest view today. Every experiment you do, we've got to figure out what's going on with the data. But by asking that question, we're asking about the probability distributions. From those probability distributions, I can make judgments about your experiment. Are there truly two different effects for A and B, or are they so close together that I can't tell a difference between your treatments? Okay, just keep that piece in your mind. This is the classic piece with regard to the central limit theorem. The key thing when I teach this, I do ask my honor students to be able to explain it in detail to see if they can mine all the different components. That's not what I'm going to ask you to do. I want you to understand what this one theorem is trying to tell you. It's telling you that the sample mean, a statistic, can be linked to a probability distribution. And because that statistic can be linked, I can make judgments of whether something is rare or common. All probabilities are telling me is should that event occur commonly or is it rare? So I should be able to make a judgment about your statistics in your data. If I will make certain assumptions, I should be able to say, you know, technically, if there's only one probability distribution out there, I would observe this type of data 90% of the time or more. Well, if you say that to yourself, you're going to say, well, that's pretty common. Maybe I should continue to believe that there's only one distribution out there. I could also come back and tell you, hey, based on the way this data turned out, the probability that I would get this type of data, given that there's only one probability distribution out there, is 1 in 1,000. What would you say? Well, that's very rare. The data does not seem to be compatible to that belief. Perhaps we should believe that there are two distributions out there, and we have evidence that there is a treatment effect. That's what it all boils down to. But it's by linking statistics to the probability distributions. That's why I say we always have to start with the probability distribution. All right, so I'm going to assume that you were taught completely wrong. Perhaps I taught you, but let's back up and try to do it all again. Key terms, and that's the other thing, is statisticians, and it's always hard when we use a lot of jargon. Let me ask you this. In a jury trial, so you'll never forget this, in a jury trial, what's the null hypothesis? What is assumed to be true before you start your experiment?
Innocence.
Or before you start your trial?
Innocence.
Innocence. That's the null hypothesis. The null hypothesis of a jury trial is the person is innocent. Do you collect evidence to prove that? No. It's an assumption. What is prosecution collecting data for, or evidence for? To get to the alternative, which is guilty. Notice those two things are what statisticians love to call mutually exclusive and exhaustive. It covers all potential possibilities. One is the opposite of the other. The same is going to be true when we set up your experiment. We're going to write out a null hypothesis. We're going to set up an alternative hypothesis. It will be about probability distributions, but they will be mutually exclusive and exhaustive. And when you're collecting the data is never to prove the null hypothesis. The data cannot prove the null hypothesis. In fact, I can't prove anything. You want to prove something, go to the math department. You need evidence and a judgment of evidence. You're talking to the epidemiology and biostats, okay? Null hypothesis is the one that is assumed to be true until evidence is provided sufficient to move to the alternative. Okay? Now, we get this crazy thing. I'm going to go out of order. Okay, I'm going to go out of order on my slide here. So, when the jury is to evaluate the evidence, what is the metric they're supposed to use? Evidence beyond what?
Reasonable doubt.
A reasonable. Thank you for not falling into the Perry Mason trap, though I'm probably the only one old enough to remember Perry Mason, who introduced the phrase shadow of a doubt. No, there are no shadows. It's beyond a reasonable doubt. Guess what? Reasonable doubt is what statisticians call type 1. When you hear people say, what's the alpha level? Or what's the type 1 error rate? That is where I draw the line at reasonable doubt. Okay? Now, in scientific journal, in scientific literature, reasonable doubt has been typically set at what probability level? Talk to me. From your experience. 0.05. 0.05. Why? Because
It's reasonable.
somebody put it in a footnote. Not joking. Somebody put it in a footnote and it caught on. There's no magic reason for 0.05. It does not have to be 0.05. Do not get married to 0.05. Do not become obsessed about 0.05. And do not be like one of my PIs who broke down and cried after a 4-year clinical trial when I reported that the p-value was 0.06. Okay? We still got it published. It's just a line, folks, okay? It's a reason, it's why you've got to understand what a p-value really is. Now, what is the p-value? The p-value is the evidence, folks. That's all it is. I said evidence beyond reasonable doubt. That should help you remember, we get these crazy rules on the board. P-value less than or equal to alpha, reject the null. Think about it. If my p-value is evidence, less than or equal than is beyond, Alpha is reasonable doubt. It's the exact same phrase. It's just written as a mathematical equation. My evidence must be rare enough for me to be able to reject the null hypothesis and include the alternative, right? That's the whole game, all of it. Now my question becomes, and this is a key thing. So we're looking for evidence beyond a reasonable doubt. When they evaluate the evidence, what do they have to assume to be true at all times? They have to assume what? What do they, when we say, when they're evaluating the evidence, they have to hold what assumption true at all times in the evaluation? The person is innocent. The question before the jury is literally this: how likely is it that I could get this type of evidence, assuming the person is innocent? So I was on the block that the person got murdered. We have evidence that David was there. My question becomes, is that sufficient to be able to say David's the murderer? Well, not if my favorite restaurant is on that block and I visit my favorite restaurant 3 times a week. It's becoming not very convincing because there's other possible reasons to be there. However, my fingerprints are on the knife. The victim's blood is in my car. The victim's blood is on my clothes. Well, those types of things just don't occur with innocent people, do they? So the evidence does not match the assumption. That's what we're doing with a p-value. Look at the key thing. I make people, and I actually tell the students, and I hold them to this in the honors class, you can't write this definition correctly, I give you a B. Period. And the most important phrase in that p-value is the probability of observing the data, or data that is more extreme, given the null hypothesis is true. Same concept as the jury trial. I'm looking at my evidence and saying, is my evidence compatible with the belief that the person is innocent? I'm asking, is my data compatible with my belief that the null hypothesis is true? Same game. There's no difference. All right, power, the key thing is there's always 2 types of errors. The one we worry about in the jury system is we do not want to send the innocent person to prison, right? So we have accidentally rejected the null and concluded the alternative, even though the null was true. The other one that frustrates people is we often let the guilty go free. That's the type 2 error. It's the accidental mistake of the person is really guilty, but we did not have sufficient evidence to get us to the conclusion that the person was guilty. In correlation, the key thing here is we'll get into correlation maybe at another date, but people interpret correlation all the time. Correlation is not whether there's an association between my height and my weight. That's not it. I can measure the association of height and weight throughout this room. Okay, if my correlation statistic is non-significant, that doesn't mean that it's not significant or there's no association. It means I can't make it a line. I'm not seeing a linear association. It doesn't behave like a line. It could be a beautiful curve. Correlation asks, is it linear? Okay. So this is, and I teach this. I confess, I teach this. It's what I call the box step. There are 4 steps in every hypothesis test. I'll walk through this regardless of every collaboration I do. Eventually there will come a time where it is time to conduct the actual statistical inference, and I'll very carefully make certain that you understand the null, the alternative, get you to the correct method. Then I'll get you the p-value, and if the p-value is less than or equal to alpha, or read it again, evidence beyond reasonable doubt, we will reject the null and conclude the alternative. And that's what you want to do because then we can say our experiment produced evidence in favor of your research hypothesis. Didn't prove it. It just provided evidence that would indicate that this is a more compatible explanation. Then we write a conclusion. But here's the thing. You can't find it in statistical literature. Every textbook shows it. Every professor in the United States that's not doing Bayesian is teaching the exact same thing. You can't find it in previously. If you go back through the statistical literature, you can't find it. In fact, I came out in 1992 and with a bachelor's in mathematics, having 4 classes in statistics and was not taught the p-value. And that was in the 90s. Was not taught the p-value. I was taught rejection regions. P-values weren't even discussed in the textbook. Where did it come from? Well, let's talk about that. So there was a very good geneticist, a very brilliant man. It's a little difficult to work with, they say. But he started the modern approach to statistical inference. His name was R.A. Fisher. You ever hear Fisher's exact test? That's Fisher. If you ever hear the F distribution, the F stands for Fisher. You ever hear things called maximum likelihood estimates? That's him. He did a ton. But he would just say, this is the way he did all his experiments. And he's the one that started everything. He would say, okay, set up a null hypothesis, calculate the p-value. He's the one that came up with the concept of the p-value. And he said, report the p-value, and he was done. There's no statement about a conclusion, and there's no discussion of a type 1 error rate. Why? Why did he do this? Because he felt like everyone should be treated like a jury member, that they should be able to be handed the p-value, and each individual person should, from their scientific perspective, say, is that convincing to me? So in other words, for me, maybe my threshold is actually I need to see 0.01. But other people might say, hey, that's 0.08. That's good enough for me. And he would leave it, and he wanted the scientific community to function as their own jury. That's what he wanted. He didn't get what he wanted. Then there's the other guys, Jerzy Neyman and Egon Pearson. We're very good at names and statistics. Neyman Pearson proposed the following things. He said, set up a null. They said you got to have the null and the alternative. You have to pick a type 1 error rate before you start your experiment. You have to say and publicly declare, beyond a reasonable doubt is right here. And then they said using the type 1, they defined a rejection region where you would actually draw the shape of what you thought the probability distribution was, depending on what your test statistic is or how your data is behaving. Could be skewed, but they would shade a little region and say, if your statistics fall all the way out here, reject. Otherwise, if it's in the other regions, fail to reject. I actually like the rejection region approach. But here's the thing. They would come back and say conclude or accept the null hypothesis. This causes me a little bit of concern. Think about the jury trial for a minute. Okay, go back to that. And this is a key thing. Gotta watch my time. Key thing. When the jury trial is over and the jury comes back in the room, and whoever the foreperson is of the jury, they stand up, bailiff walks over, takes a slip of paper, walks it over to the judge looks at it, hands it back to the bailiff walks back to whoever the foreperson is, person stands up and says, we the members of the jury, let's start with the easy one, guilty. Okay, guilty's done. Now let's go to the harder one. What does the person have to say? We, the members of the jury, find the defendant. What's the phrase?
Not guilty.
Why?
Because they can't conclude innocence.
Why? You're going the great rabbit trail. Let's go. You're doing great.
Wait, what did he say? They say what?
They never say innocent. They say not guilty, and there's a specific reason for it. And you've already hit both of them. I'm just trying to draw it out a little bit further. You said you can't prove innocence. I said, why can't you prove innocence? Because it was assumed in the process. So you cannot say, I personally do not ever say I accept them all. I simply say we failed to reject it. That's the strongest statement I'm willing to make. Okay? Now, what happens is this. Where did null hypothesis testing come from? Notice Fisher never said anything about the alternative hypothesis test or the alternative hypothesis. He never brought up a type 1 error rate in all of his research. But yet, Damon and Pearson never talked about p-value. But yet now we teach it as if it's just one big blended subject. Why? Because they really hated each other. I mean, they really hated each other. And just for convenience, we blended it all together. It's a bastardized version. What modern statistics is these two very different ideas that just got slammed together. And so when you find it confusing, what you're finding confusing is where they fought. It's where they disagreed. It's why some people will say, I can accept the null, and other people will scream, no, you can't, because some of them are still relying on Neyman Pearson philosophy, others are relying on Fisher's philosophies. So does this mean it's you? I just told you the truth. I told you what most statisticians will never tell you. Does it mean it's useless? No. Doesn't mean it's useless. It means you've got to recognize the limitations. Okay? And modern science has gotten to where everything is tailored down to what's the p-value. I can be convinced with a graph. I don't have to have a p-value. Sometimes if I can just look at a graph, the data is going to be convincing enough for me to say, I think there's reasonable statistical evidence there for us to pursue that further. I really don't care that the p-value is 0.10 or 0.009. I think we should go with it. I know for a fact, under certain limitations, asymptotically, the p-value can't get below a certain value. Your sample size is no more than 6. There ain't much I can do with it. You may never get a p-value below 0.05. Why would I use it? It's foolish. Okay? Please keep that in mind. You do not have to always use a type 1 error rate of 0.05. And then the piece of the story that you want to know, Fisher got pressed. Fisher kept getting pressed with what is convincing evidence for you, sir? What is convincing evidence for you? And that's the footnote story. He literally says in one of his articles, or in a manuscript actually, in a chapter, he says, for some, it will be 1 out of 100. For others, it would be 10 out of 100. For me, it suffices that it's 5 out of 100. It's like somebody chiseled it in stone. It's not, folks. In fact, I'm very comfortable with just taking the p-value and reporting it and letting you make the judgment. Let's have a scientific discussion about it. And then before we get so engrossed in the p-value, let's talk about some graphs. Let's talk about some of the things that could be explaining what's going on. We just have to be very careful because, again, I do take it as a responsibility to put out very good science. And now I'm going to come down the home stretch. We're not going to get all the way through it. But it's key that you understand what a p-value is and what it is not. Okay? You must resist the urge to interpret it the incorrect way. And one of the favorite games it's an odd game, but it happens almost every year at the big statistical conferences. There'll be a talk about, this is the interpretation that was put in. I'm just going to throw one out. My wife's a clinical psychologist, so she'd be mad at me. The Journal of Clinical Psychology interpreted the p-value this way. Look how far off they are. but it's key that we've got to understand you can't overinterpret it. So I'm going to play a game with you. Let's play true-false for a minute. A researcher reports that the p-value from his or her hypothesis test is 0.01. Based on this information, the researcher has absolutely disproved the null hypothesis. True or false? Why?
1 out of 100 times, it's,
That's exactly right.
I mean, well,
That's the exact correct interpretation. Even if the null hypothesis is true, it would occur 1 out of 100 times. Anytime you do an experiment and use inferential statistics, you must acknowledge you have the possibility of type 1 and type 2 errors. It's decision theory. So you cannot at any time say, I have absolutely proved anything. I regret to tell you, it is true. We have innocent people in prison. We have made type 1 errors. Next one. This is a very common interpretation. A researcher reports the p-value is 0.01. The probability the null hypothesis is true is 0.01. True or false? I got one definitive head shake. I need more than one player in the game today. How many want to say that's false? How many want to say, no, it's true, David? Let's go back to false. Okay, how about I'm not going to play your game, Dr. Red. If you want truth, talk to the philosophy department. Don't come to me. If you want proofs, go to the math department. Don't come to me. Okay? I cannot, the p-value has nothing to do with truth. Okay? But people will put this in literature, scientific literature. No! We already know this. It's absolutely proved. No, again, I haven't proved anything. I have either evidence for, or evidence that is compatible, or evidence that is not compatible. That's all it boils down to. Common one, especially in psychology. Is this correct? There is a 0.01 probability he or she is making the wrong decision. True or false? This is very common in psychology. It's false. It's false. Because what you've done there is you are confusing type 1 error rate and p-value. Keep in mind, if I tell you the p-value is 0.01, the literal interpretation is 1 out of 100 times I would have gotten this data or data even more convincing, assuming the null hypothesis is true. Just that is. Under the belief and under the evaluation that the null hypothesis is true, this data or data more extreme would have occurred 1 out of 100 times. Leave it to the people to determine if that's convincing or not. So that one's false. I'm going to let you read that one. This one's also in the literature. Based on this information, the probability that the null hypothesis is true, given the data, is 0.01. Sounds good. True or false? Y'all don't trust me, do you? We gotta have a vote. True or false? Chris, true or false? You didn't hear me. True or false? Come on.
False.
False why? Why?
Everything else was false.
So part of the probability distribution, there it is false. So far, the probability distribution has been all false. Why? This is something that people want to do. They're always trying to take the p-value and say it's a probability about the hypothesis. It's not a probability about the hypothesis. It's a probability about your data. The p-value is always about the probability of the data under an assumption about the hypotheses. This inverted the two, but this is a common mistake. They say, oh, the probability of the null hypothesis being true given I saw this data. No, backwards. It's backwards. You've got to reverse it. What about this one? That's the correct one. It's always going to be, this is it's the probability of the data, or data more convincing, when under the assumption the person is innocent, or under the assumption that the null hypothesis is true. So that one is the last one and it's false. Now the fifth one that I gave you is, you heard me say Bayesian. Keep in mind, statistics is a huge broad field. We use about this much of it. Obviously, in clinical science, in clinical research, and in inferential, you know, this much of it. There's a field that if you're willing to make more assumptions, and this is the key thing, people want to be Bayesians, and I have no problem being Bayesian. You just got to be able to say, I'm making these extra assumptions, and tell them why you believe those assumptions are realistic, okay? But if you're willing to make more assumptions, you are able to get to, with added assumptions, the probability of the null hypothesis being true, given the data, but you've got to make some strong assumptions. I have a little bit, I have done it, but I wrestle with it. So let's just walk through a basic teaching example to try to pull all these things together. And I'm going to dismiss us at 9:15, if everybody's wondering, 9:15. That'll give us enough time to get ready for the next one. And then I'll be here next week. And of course, Ryan can get you in touch with me, and I'll be here most of the summer if we need to go through any of the other pieces. So, you know, cholesterol levels, basic things. If we wanted to compare men and women, that's one basic question. When you ask for gender differences, what are you asking for? You're asking, is the probability distribution different between the men and women? That's all you're doing. But evidence of that would appear in the mean cholesterol levels. It would mean that the probability distributions are misaligned. They line up perfectly, they're probably one probability distribution. They're misaligned, probability 2. And we say, okay, we're going to do this experiment. We're going to take 10 men and 12 women. We will use alpha equal to 0.05. What you would get summary statistics. This is where you would begin your consultation. You would get the data. You would sit down with a statistician. The statistician would immediately say, how many men do I have? How many women do I have? Where are the sample means? And you've got one at 220, another one at 215, so there's a difference of 5. Question becomes, from a statistical standpoint, 2 things to take home from this message. From a statistical standpoint, it could be a statistically significant difference. Hear me well right now. Just because something is statistically significant does not make it clinically relevant. Did you hear what I just said? I can find things all day long and declare p-values below 0.05 all day long. And it may not mean a darn thing clinically. And that's why there's always going to be team science, a discussion here. This is just a teaching example. But the question becomes, based on all the data, is the data providing sufficient evidence or sufficient information that if I summarized it, I would be willing to conclude there are 2 probability distributions, or is there 1? And here's the key thing. Statisticians always have to use their Greek symbols or else we get kicked out of the club. mu1 equal to mu2, all I'm saying is do the two probability distributions line up at the exact same point, because if mu1 equal to mu2, they're right over each other. And that's all it's telling me. The two probability distributions are hovering right over each other. Mu1 not equal to mu2 means what? Yeah, but they could be this far apart. Or they could be this far apart. Or they could be this, or they could be this far apart. So there's a lot of possibilities under that alternative. The little bit that doesn't really matter, or the big pieces that really do. And we've got to ask ourselves, how do we get there? Well, statistician sits down, maps out the data, checks all the assumptions with you, walks you through all these things that you do not have to. You need the statistician because they're going to know that they should look at a normal probability plot. They know they're going to double check for outliers. They know if outliers are there and they can't be removed, that we've got to do a fallback procedure. All of these different avenues, assuming the data is clean, we come down, we get a test statistic, and we get a p-value. And we end up saying the p-value is 0.01, the alpha level is 0.05. Is that evidence beyond reasonable doubt? Reasonable doubt was defined at 0.05 to begin with. Evidence beyond a reasonable doubt? Yes. How would you interpret it? What would you conclude? That's what I'm asking you. Before we go to the next slide, what would you conclude?
We have evidence in favor of the
Alternative hypothesis, which states the probability
the
distribution,
opposite,
the probability distributions for, or the mean levels for men and women differ, just simply differ. And that's all you can say. But I would be very careful, and I try to work with my investigators to put, even if you can't get it in the journal, get it in your documentation, that there's sufficient evidence, and then state what that evidence is. Put the p-value right there. At alpha 0.05 to reject the null hypothesis and conclude that the mean cholesterol levels differ between men and women. And then I typically like to make certain that to help anchor the discussion so that we don't go too far in our interpretation, simply say that the probability of observing this data or data more extreme, assuming there is no difference between, assuming no difference would be only 0.01. The truth, and here is the truth. I told you, I'm talking about the truth of statistics, not the truth of your hypothesis test. The truth of the statistics. At the end of the modern hypothesis test, you are left with the probability of the observed data or data more extreme, given the null hypothesis truth. That's all you've got. Don't overinterpret it. Don't let that be the sole thing that you're using to try to convince the scientific community or the scientific jury. Come with graphs. Come with your scientific premise behind your hypothesis. Just don't let it boil down just to a p-value, please. And that's why I said my best advice is not to get just so ingrained. I collaborate with people all day long. They're more interested in that one value than all the graphs I could ever go. And this is an absolute true story. We did a very large 7-year study. The p-values were all significant. And the lead PI was frustrated because it wasn't having the person had done the presentations at national conference. She didn't get the response she thought she would get from the scientific community, because it was pretty large effect. And I looked at her and I said, well, why don't we do this? I said, let's stop using the p-value and just get up and explain the following graph. I handed her a graph. And I said, by the way, I guarantee you that this one graph, the minute they see it, get the paper published. It got accepted on the first go around, and that's all she uses now, is because the graph is that much more convincing than the p-value. Okay, so don't get caught up in p-values alone. It's important to understand the forest, and I've tried to explain the forest, but the scientific community is going to keep trying to push you toward it. Please, statisticians are geeks. My wife will tell you that all day long. We love to have t-shirts that say absence of evidence is not evidence of absence. Why do we play these riddles? Because we're trying to get people to understand just because you failed to reject the null doesn't prove the null. Okay? If your objective is to prove two things to be equivalent, that's a whole different game. And we have to have special meetings on how to go about that. My advice is, even though I've focused on one thing, when you meet with a statistician, the first thing you need to say, or a methodologist, is, can we discuss the whole toolbox? Talk to them about all the different methods that could be used to summarize this data. Talk to me about all the different graphs. Talk to me about the different hypothesis tests that would be appropriate. And then you need to be able to come and discuss what's being measured and what's clinically relevant, so that we don't get into the trap of producing and publishing statistically significant but clinically irrelevant stuff. Okay? All right, some references. Ryan will send these out to you right on time. 20 seconds to go. These are fun. They are not statistical theory. I would not do that to you. These are some interesting ones called mindless statistics, talking about how people just blindly follow the p-value. The other one, my favorite one, the earth is round, we have statistical evidence, p is less than 0.05. No, we've got more than that. And ironically, between friends, this is why you use it as a tool but not your only tool. R.A. Fisher, after the whole thing was done near the end of his life, made two comments that I actually, one I love, one I don't love, but it makes me think every day. R.A. Fisher made the comment to contact the statistician after the experiment has been conducted and all the data has been collected is to request a post-mortem examination of your experiment. The methodologist will tell you what the experiment died of. So it's not find the statistician after it's over, it's find the statistician before you begin. The other thing he said is, at the end of his career, he literally said, I regret that the p-value is being used in a way I never intended. Okay, so keep that in mind. All right? And with that, like I said, I'll be around. I'm going to do my best to come every week, except for the 1 week I've got to be in Mobile. And if you've got questions, easy enough to find me through the CCTS and also through the Biostatistics department.
So is this going to be on the research comments, your presentation? Good.
All right, thanks everybody.
Thank you.
You're welcome. I can sit down and talk to you about spec size. Do you have any